100,000 light years. No problem, right? Maybe we should start by measuring a single light year.
A light year is simply the distance that light can travel in a year. Light travels at an incredible speed, 300,000 kilometers a second. And if you multiply that by the number of seconds in a year, you get about 10 trillion kilometers. So the distances in astronomy are so huge that we actually have to use light years in order to measure the distances just between stars.
Another way of looking at this is that a beam of light traveling 186,000 miles per second would still take 100,000 years to travel from one end of our galaxy to the other. In the Sun's 4.5 billion years of life, it has orbited the center of the Milky Way a mere 20 times. Despite these great distances, objects within our universe collide all the time, as they have since the universe was young. Galaxies within the universe began forming hundreds of millions of years after the Big Bang, as clusters of stars and interstellar gas began coalescing due to gravity. These early galaxies were small, just 1/10 the size of the Milky Way.
The very first galaxies to have formed in the universe were small galaxies, dwarf galaxies. And as time went on, these small building blocks combined to make bigger and bigger galaxies as a result of mergers and accretion.
These dwarf galaxies found themselves, relatively speaking, caught in a traffic jam in the early universe.
In the past, the early history of our universe, interactions were much more common than they are today because galaxies were so much closer together.
As small galaxies collided, they combined into larger galaxies with defined shapes. The Milky Way galaxy, home to our solar system, is a spiral galaxy. Other shapes include elliptical galaxies and lenticular galaxies, a cross between the two. Astronomers owe these galaxy classifications to Edwin Hubble, the namesake for one of NASA's great observatories, the Hubble Space Telescope.
I think Hubble had a fun task, if you will, that there wasn't kind of a definitive, here's the classification system, so he got to make it up.
Hubble took on the astronomical task of categorizing galaxies.
What you look for is how to take care of 90%, to classify 90% of the objects there. And so you don't worry about all the strange ones.
What happened to the other 10%? Everything else went into the irregular category.
They're throwing off big tidal tails of debris, or there are galaxies that just look like a train wreck.
For years, that's where these peculiar formations sat. But the question still stood: what could have formed these strangely shaped galaxies? And could this have something to do with cosmic collisions?
It wasn't really a big topic at his time. I mean, just understanding spiral galaxies and elliptical galaxies was in its infancy.
Yet even as Hubble was more interested in sorting the majority of galaxies, he felt the ones labeled irregular warranted more attention.
It was roughly a couple decades after, when he did most of his work, that people started working and thinking about the irregular and peculiar galaxies.
Scientists wondered what made irregular galaxies look the way they did. One theory held that they were really snapshots of violent disruption and chaos.
There was kind of a debate, say 20, 30, 40 years ago, of whether these things were colliding and merging as we understand them now.
Today, astronomers continue to use this irregular category.
And irregular is kind of a catch-all term. It refers both to little galaxies that have been so disrupted by their star formation, punching holes in their gas, that their shape is very irregular. But it can also mean galaxies that have been very highly disrupted, for example, by collisions. It incorporates a wide variety of different types of galaxies.
The strange shapes of some irregular galaxies can be explained by the effects of gravity on a galactic scale. The largest objects in the universe merge in a head-on collision. Irregular galaxies are proof that these giant clusters of stars collide. They are the evidence that the universe is racked by destruction and pandemonium. But what happens within galaxies? What other types of collisions occur? And how can we see them? Next, colliding stars leave their fingerprints all over the universe, and yet astronomers have yet to catch them in the act.
The Gadget Show has got a special treat for you.
Konnichiwa.
It's going global.
It's gonna be awesome, dude!
On a hunt for the world's sexiest gadgets
32 miles an hour on a brain-controlled skateboard.
and coolest tech.
Excellent.
All new Gadget Show World Tour starts Monday at 8:10, exclusive on Discovery Science. Wheels made out of chainmail, robots that play baseball, and houses built from trash.
Welcome to my luxury dumpster home.
Join Dr. Basil Singer and find out how technology works in mysterious ways.
Off we go. That's cool.
All new How Tech Works starts Monday at 8:35, exclusive on Discovery Science.
This program contains extraterrestrial activity and two guys called Steve and Jeff.
We are the first humans ever to see this visitor from outer space.
What looks like rubble to us is a gold mine to them.
1, 2, 3. Woo! What could be more mysterious and exciting than looking for lost bits of the universe that have landed on Earth?
A new season of Meteorite Men. Saturday from 9 on Discovery Science.
Irregularly shaped galaxies are evidence that galaxies collide, but do other celestial objects crash into each other? Our universe is both a nursery and a graveyard, host to an epic war between massive celestial bodies. Imagine this fictional scenario. Almost 3,000 light years from Earth, two sister stars have been sharing the same orbit for millions of years. Over time, they've grown closer, circling each other at nearly the speed of light. Then slam. In milliseconds, they are destroyed, sending out a shock wave that encompasses the Earth, decimating half our ozone layer and killing everything in its path. This is what some astrophysicists theorize will happen if a type of star called a neutron star collided near Earth. For astrophysicists, 3,000 light years is near.
There has been a suggestion that one or more of the mass extinctions that happened to life on Earth occurred because of such an event.
Some of the most violent stellar collisions occur between neutron stars. Neutron stars are born of remnants of older giant stars that have run out of fuel.
Gravity causes the whole thing to collapse. In the center, an extremely dense object forms. It's so dense that the electrons get pushed into the protons to make neutrons. The neutron star that forms at the center is the remnant, the ashes of that star.
But these ashes have some life in them, and after their creation, some neutron stars orbit each other in a gravitational embrace called a binary pair. For millions of years, the stellar siblings orbit each other up to 1,000 times each second.
They will be emitting gravitational waves which drain away energy from the system, getting them closer and closer and closer together until ultimately they get so close together that there's no more stable orbit for them to orbit on.
When they finally collide, they release more energy than our sun would produce in its lifetime. Yet the collisions are too fast for telescopes to capture.
For neutron stars, the whole collision is over in about 1,000th of a second. Then it's done. Once they touch, they go splat, you're done.
Their collision sends a massive shock wave through space. From Earth, the collision is detected as a short gamma-ray burst, or GRB. A GRB is a short-lived yet powerful event. evidence of one of the most violent collisions in the universe. But scientists have only recently begun to fully understand what GRBs mean.
There are little gamma ray flashes that happen a couple times a day in the sky. And we pretty much monitor the whole sky for gamma rays all the time. And these have been known for about 40 years now.
The U.S. Air Force had actually detected GRBs years before the scientific community even knew they existed.
Gamma ray bursts were discovered completely by accident by military satellites and came as a result of the test ban treaty in the 1950s under Dwight Eisenhower.
The nuclear test ban treaty begun under President Eisenhower resulted in the creation of military satellites designed to search for nuclear explosions. The Air Force launched the first Vela satellites in 1963. This series of satellites was built to detect, among other things, gamma rays, using gamma ray detectors.
The clouds of radiation that would be released in such an explosion would be releasing gamma rays. Those gamma ray detectors were the first ones to detect cosmic gamma ray bursts.
In 1969, Ray Klebsaddle, an Air Force analyst, found strange spikes in gamma rays within the Vela data that, because of their intensity and duration, could not be attributed to either the Earth or the Sun.
So they knew they must be coming from somewhere out there.
By 1973, when Klebsaddle finally made his research public at an American Astronomical Society meeting, he had at least 16 confirmed gamma ray bursts. But more sophisticated equipment would be needed to fully observe GRBs. In 1991, NASA launched the Compton Gamma Ray Observatory, a space satellite dedicated to detecting GRBs. What scientists hoped to do was catch a gamma ray burst in action in order to determine what it was. Could GRBs be a type of cosmic collision?
The Compton Gamma Ray Observatory detected a couple of thousand of these gamma ray bursts and established that they do in fact happen all the time. But what was really needed is a way to quickly identify the gamma ray burst and quickly get a telescope on there to take a picture, because they fade away quick.
In fact, GRBs fade completely away within just a few days.
5, 4, 3, 2, 1, have ignition, and we have liftoff of NASA's SWIFT spacecraft on a mission to study and understand gamma ray bursts throughout the universe.
In 2004, NASA launched the aptly named SWIFT telescope to better track and react to GRBs.
SWIFT is a satellite with a big gamma ray detector that is relatively good at detecting the direction from which the gamma rays are coming. As soon as it sees a gamma ray flash, it radios the location to the ground, and then it starts swiveling an X-ray telescope to that same location.
In 2005, SWIFT detected a burst, and in less than a minute, it repositioned itself to observe its afterglow. Meanwhile, SWIFT sent the GRB's coordinates to its network of ground telescopes. One of those telescopes is located near the summit of Palomar Mountain in San Diego, California. The Palomar Observatory combined its data with calculations from more than a dozen other institutions. Together, they were able to identify a probable cause of the short GRB, a collision between neutron stars. Since stellar collisions occur within a second to a few hours, most of what happens remains a mystery.
The actual collision event is a very short-lived thing. It's for that reason that it's unlikely we'll ever in our lifetimes be able to capture a couple stars in the process of colliding. But what you can do is you can look at the aftermath.
So, while astronomers have never actually witnessed a stellar collision, they know they exist by examining the ruins of these brutal star wars. Neutron stars are not the only stars that collide in violence and destruction. Even infant stars can create cosmic havoc. Stars lead a violent existence, and not just neutron binary pairs, but virtually all stars starting with the nature of their formation. The turbulent life of a star begins with the death of a molecular cloud.
It's a dense region of interstellar gas. In these clouds, stars form, planets form, our own solar system formed.
Molecular clouds grow larger as the force of gravity from them attracts more gas and particles until their density gets so large they collapse to form stars. An exterior force like those caused by a cloud collision or the shock waves of a supernova can also cause the clouds to collapse.
As it collapses, it gets denser and denser in its center. It gets hotter and hotter in its center.
Recent research places the first star formation at only 100 million years after the Big Bang. Some of those stars astronomers believe can still be found in our own Milky Way galaxy. Today, researchers focus on compact groups of stars called globular clusters. For those researchers studying stellar collisions, globular clusters are the place to look. These dense collections of stars serve as an ideal stellar battlefield.
Just like if you're walking down a street in a crowded city, you bump into people. And stars are close enough together and they're crowded enough, they bump into each other.
With about 100 billion galaxies in the universe, and with each one containing about 30 globular clusters, the number of stellar collisions can be staggering.
If you count up all the galaxies in the universe, hundreds and hundreds of billions of galaxies, and ask how many regions do they have where stellar collisions could occur, it starts to be a very large number.
It was a mystery within globular clusters that led astronomers to one of their biggest discoveries. Discovered in 1953, highly luminous stars in globular clusters stumped researchers for more than 40 years. They named the strange stars blue stragglers.
These blue stragglers have some peculiar characteristics to them. They're called stragglers because, unlike other stars of the same mass in that cluster, they haven't yet gone on to later stages of evolution. So they're stragglers and they're blue because they're hotter than the other main sequence stars in the cluster.
It seemed blue stragglers had discovered the stellar fountain of youth. Scientists wondered how that could be possible. NASA's Hubble Space Telescope, launched into orbit in 1990, played a key role in answering that question.
Hubble's resolution is so fantastic that if you could look with it from New York to Tokyo, you could see two fireflies. This is how good the resolution of this telescope is.
Hubble's optics captured detailed images of blue stragglers, allowing scientists unprecedented access to their secrets.
So by looking at these individual stars, it was able then to measure the properties of these stars. For example, their mass, how fast they rotate, their temperature, and things like that.
Astronomers discovered the blue stragglers' high mass, fast rate of spin, and high temperature could only mean one thing.
A blue straggler, we think today, is most likely the result of a merger of two stars. And those mergers could have happened via collisions, direct collisions, two stars colliding with each other, or two stars that were in a binary system where they rotate around their center of gravity.
In one example, a main sequence star plows into another at about 500,000 miles per hour. It burrows into the other star, setting off a wave of gas and debris into space. Immediately, the stars will swell and ferociously burn energy. It can take 10 million years for the stars to overcome their violent merger and settle into a blue straggler.
This was the first evidence that we had that stars really could collide with each other. And this is one of the more remarkable things that stars have been found to do.
It took decades for the idea of stellar collisions to move from theory to full-blown reality. But where galactic collisions are concerned, slamming stars are just the tip of the iceberg. Cosmic collisions are the rule, not the exception in the universe. And at every level, right down to the dust that wafts through space.
In our own solar system, all the planets, all the objects that we see were built by collisions. Dust colliding to make sand, sand colliding to make pebbles, pebbles to rocks, boulders to planetesimals, asteroids to planets. So our own origins are from collisions.
Galaxies can be violent places, the locus of death, birth, and rebirth.
The Gadget Show has got a special treat for you.
Konnichiwa.
It's going global.
It's gonna be awesome, dude!
On a hunt for the world's sexiest gadgets.
32 miles an hour on a brain-controlled skateboard.
And coolest tech.
Excellent.
All new Gadget Show World Tour starts Monday at 8:10, exclusive on Discovery Science. We've got something special for you. In fact, we've got lots of things. Some are supercharged. Some are super smart. And some are just super cool. And they're all bursting to come out and play.
Off we go. That's cool.
A season of the greatest gadgets.
How cool is that?
And the most tantalizing tech around.
It's just bananas. And that was incredible.
The Gadget and Tech season starts Monday from 8:10 on Discovery Science.
Galaxies collide, and so do stars within galaxies. But are there other objects that can go bump in the night? Cosmic collisions aren't limited to large bodies crashing into each other. Sometimes a collision can occur with jets of energy, deadly energy. Lethal radiation spews out of a supermassive, mysterious object called a black hole, a quasar. The beam from what scientists have dubbed the Death Star galaxy is slamming into a smaller neighboring galaxy.
What's actually happening is a jet is coming out of one black hole and it accelerates close to the speed of light, and that jet strikes a companion galaxy that's swung into the path of that jet, and that wreaks all sorts of havoc for any inhabitants or any Earth-like planets in that companion galaxy.
The ones that are close enough would be sterilized. The ones a little bit further out would have their atmospheres damaged.
These are the really extraordinarily acts of violence by a supermassive black hole.
It sounds like science fiction, but it's science fact. Luckily for our galaxy, this cataclysm is taking place in galaxy 3C321, a galaxy far, far away, 1.4 billion light-years distant. This is the first time astronomers have observed a black hole jet punching into a companion galaxy. But this event raises many questions, beginning with what is a black hole? And are we Earthlings in danger from a death ray? Black holes aren't really holes at all, but instead are incredibly dense and massive objects. Black holes are so dense, their gravitational pull so strong, that nothing can escape them, not even light itself. It takes observations from multiple telescopes to make a complete picture of this unique phenomenon.
It's only by combining information right across the electromagnetic spectrum that we can begin to study black holes with great precision.
Part of that picture was taken at this telescope, the VLA, or Very Large Array, in New Mexico. The VLA is a radio telescope made up of 27 dish antennas, each one of them weighing 230 tons. The antennas are arranged in the shape of a Y, and each arm of that Y is 13 miles long. The VLA is especially adept at observing black holes, such as the one in our own galaxy.
That thing is about 4 million times more massive than the sun. and it creates all kinds of phenomena, but gas and dust between us and that black hole obscures all of that to visible light telescopes. Just like a visible light telescope is collecting light waves to make an image, we're collecting radio waves to make an image.
Optical and short wavelength radio cannot see into the inner parts of these regions. Radio can. And radio astronomers of long wavelengths, such as this facility, can peer into the inner parts of these regions that are obscured to other wavebands.
Most galaxies have supermassive black holes at their centers. They can be 1 million to 1 billion times the mass of our sun. Despite their mass, we initially couldn't see black holes. So how did we eventually know they were there?
As material flows in towards a black hole, it's much like water going down a bath plug. It goes down, and it spins around, and essentially through frictional forces, that friction generates heat and it generates light. And that light is so intense and so energetic that it forms X-rays.
It was the disappearance of objects in this drain that led 18th century astronomers to suggest the existence of an invisible star.
In 1783, the Reverend John Mitchell laid out beautifully the idea of an event horizon. Mitchell showed that a body that's very massive with a small enough radius would have an escape velocity that is the speed of light. It would trap the light and be invisible, be dark. That is the idea of the event horizon.
John Wheeler, a close collaborator of Albert Einstein's, coined the phrase black hole in 1967. It was then still a theory. Scientists hadn't even realized that they had already found their first black hole. The evidence was X-rays, invisible energy produced by black holes.
In 1971, the X-ray source was identified with a very massive, giant blue star. Later in 1971, we were all startled to find that this optical star that was so massive was orbiting the X-ray source at a very high velocity. This high velocity means that the X-ray source is more massive than 3 times the mass of our sun. This essentially established it to be a black hole.
Probably the biggest boon to the study of black holes came in the form of another of NASA's great observatories, the Chandra X-ray Observatory.
We've often been asked, why don't we do X-ray astronomy from the ground? Because, of course, it's riskier, more expensive, and challenging to put your telescope up into space. The Earth's atmosphere is actually very opaque to X-rays. It blots out all the X-rays that come from stars and galaxies that are far off. So if we want to do X-ray astronomy, we have to go into space. And Chandra is the most capable X-ray telescope that we've had. Chandra is particularly suited for studying places and objects in the universe where violent conditions, extreme conditions, generate X-rays as a primary signature. We're talking about, for example, matter falling into a black hole, stars exploding as supernovae, or galaxies colliding. And it's this kind of cosmic violence that Chandra is particularly adept at studying.
X-rays are present whenever a celestial object produces large amounts of heat. Neutron stars and black holes can create X-rays 100,000 times the strength of the X-rays the sun produces. Chandra was pivotal in helping astronomers understand what's occurring in the Death Star galaxy.
So Chandra allowed us to see the central black hole sources. It allowed us to determine the presence of this X-ray jet. And it's this jet that gave rise to the name of the Death Star galaxy, because the jet points directly in the direction of the companion galaxy, and you can actually see the effects of that radiated beam of energy and particles as it hits the neighboring or companion galaxy.
Like most cosmic collisions, there's a silver lining. Once the Death Star jet has devastated the nearby galaxy, it will likely unleash a new round of star and planet formations. It's all part of the universe's cycle of life and death.
Black holes aren't necessarily these cosmic cannonballs. They don't necessarily run through the universe, sucking up everything in their path. In fact, one of the ultimate legacies of black holes could actually lead to the creation as well as destruction of life.
our solar system has managed to avoid death rays only to be thrust into a galactic calamity of staggering proportions. In the distant future, our galaxy, the Milky Way, and its neighbor Andromeda will collide. But will this collision be a source of creation or destruction? But what could a galactic collision like this mean? It turns out that the greatest danger comes from collisions with those thermonuclear reactors, also known as stars.
If a star comes sufficiently close to the solar system, it may send comets in our way. If it comes even closer, it may disturb the orbit of the Earth around the Sun, and so life as we know it will cease to exist, because either all the water will get evaporated, or else it would freeze if we are sent out away from the Sun.
The collision between the Milky Way and Andromeda was destined from the time in the early universe when these two galaxies were born side by side.
Things that merge are born bound and eventually come together. Things that are born unbound generally don't merge, they just separate.
Most galaxies are diverging in the expanding universe.
And all galaxies, it turns out, that are far away from us will recede away from us and disappear from view within a finite amount of time. The only exception is the Andromeda galaxy, the nearest neighbor, our sister galaxy.
Andromeda and Milky Way, their gravity has actually, at some point in the past, reversed any receding velocity between the two of them, and they're now approaching one another because of that mutual attraction.
We're actually on a collision course. Seem to be coming straight at each other, and it's looking pretty bad for us.
The Andromeda galaxy, within about 5 billion years, will collide with the Milky Way galaxy.
But what's the evidence of this coming collision? It turns out that the light signatures that Andromeda gives off are the strongest evidence of its approach.
It's the same stuff that makes the fireworks colorful. You look for a particular color, and you know it's coming from iron or oxygen or sulfur or something, and you know what color it should be, and then you just see what color it seems to be. Is it bluer or redder? If it's bluer, it's most probably because it's coming straight at you, and if it's redder, it's because it's going further away. You look at Andromeda, and it's blue shifted, and the speed at which it has to be moving is a few hundred kilometers per second. So it's coming at us, and coming at us fast.
But wait, a collision that destroys life on Earth is only one possible scenario, and not at all the most likely one. So what will actually happen in 2 billion years when these two galaxies begin to approach each other? Because galaxies are incredibly massive, and the distances between them so great, a collision takes billions of years from start to finish. As a result, astronomers can only observe snapshots in the sky. To understand the whole process, they rely on simulations.
Every snapshot we get of a galaxy collision in the universe is really just one piece of a very long sequence. And so these simulations allow you to piece together the various situations and see how it develops, from approach to passing by to the tidal tails to smashing together to mixing all up.
In the 1970s, astrophysicists and brothers Alar and Yuri Tumray created the first simulations of colliding spiral galaxies. Their simulations duplicated features that have since been observed in colliding galaxies. Their sequence detailing the steps from galactic approach through merger has become known as the Tumray sequence. Today, Frank Summers, an astrophysicist at the Space Telescope Science Institute in Baltimore, Maryland, uses state-of-the-art visual effects programs and banks of computers to compress galactic collisions into simulations depicting 10 million years of galactic action per second. It all starts with the approach. Two spiral galaxies draw near to each other.
You can see here that just before they start to crash, there really isn't any tidal distortion, which I thought was really strange when I looked at the visualization.
Right, they're still pretty symmetric there. It's only when you kind of start sending out these tidal tails that they would be put into the Tumray sequence.
Okay.
And then you can kind of watch as it comes along here. They start kind of first pass, and then they come back together.
The simulation shows the tremendous gravitational attraction between colliding spiral galaxies. Vast strings of stars and gases, known as tidal tails, are thrown out into distant space. This dramatic stage can be verified by images of colliding galaxies, like the antennae galaxies and the mice.
The Gadget Show has got a special treat for you.
Konnichiwa.
It's going global.
It's gonna be awesome, dude!
On a hunt for the world's sexiest gadgets.
42 miles an hour on a brain-controlled skateboard.
And coolest tech.
Excellent.
All new Gadget Show World Tour starts Monday at 8:10, exclusive on Discovery Science.
And despite everything else going up in flames, it survived.
Weird.
I was told I'm part human and part extraterrestrial.
What?
I couldn't believe what I was listening to.
Can science separate the unbelievable?
No one knew what was going on.
From the downright impossible?
This creature is something that you have never seen before.
Or is it just weird, or what? The new season, Thursday at 9, exclusive on Discovery Science.
Wheels made out of chainmail. Robots that play baseball. And houses built from trash.
Welcome to my luxury dumpster home.
Join Dr. Basil Singer and find out how technology works in mysterious ways.
Off we go.
That's cool. All new How Tech Works starts Monday at 8:35, exclusive on Discovery Science.
Astronomers predict that the Andromeda-Milky Way collision will progress with the same shearing stage.
The tidal tails are basically the outskirts of the Milky Way being ripped apart. The Milky Way is a thin, fairly fragile, delicate galaxy. And the Andromeda is actually bigger than we are and more massive. And when it zooms past us originally, its gravitational field is going to tear at the Milky Way.
But as the two galaxies come together in 2 billion years, their approach will look less like a collision and more like the swing of a pendulum, momentum carrying the galaxies past each other and gravity drawing them back.
They'll keep on moving because of all this momentum they've built up. And as they move apart from one another now, the Andromeda Galaxy and the Milky Way Galaxy will start to slow down because of the gravitational attraction between them. The recessional velocity will decrease until ultimately they turn around and come back for another passage past one another.
4.5 billion years from now, once again the galaxies swing toward each other. This time, it will be a direct hit.
These beautiful disk structures of these two spiral galaxies are probably going to get totally destroyed. They'll be pulled out into these long tidal tails, and then when they come smashing together, well, the orbits of all the stars will randomize, and what you're going to end up with is more of an elliptical shape in the center, and these big long tidal tails that'll come raining back in over the course of billions of years.
The collision has become a merger.
And then the central parts here are now merging together, and now you have just a central, kind of one single galaxy at the center. And so the outer tidal tails would kind of dilute, and you'd come back in another, 500 million years or so, and you'd see one galaxy. You can see how they merge together here, and so now you really have essentially one core. You still have some tidal tails. Those will tend to fade with time, and so if we take this a little bit farther out there, we would think we have just one object, and it would look pretty much like an elliptical galaxy at that point.
Astronomers speculate that the elliptical galaxies in the universe are the product of galactic collisions like these. But what actually happens inside colliding galaxies as they go through this violent process? And what does it mean for our planet as we endure the cataclysm? The images of colliding galaxies are ethereal. Tidal tails stretch out like spider webs. Galactic cores orbit each other locked in attraction. But do these beautiful images mask wholesale destruction? Stars slamming into each other, planets crashing, moons atomized into space dust.
One of the coolest things about galaxy collisions is that when these huge galaxies smash together, the stars don't. If you take a star and another star, the distances between them are millions of times larger than the diameters of the stars.
And during this galactic collision and ultimate merger, what are the chances that Earth will be smashed to bits? According to astronomers, quite low.
Each star has something like the solar system around it. Even the space between those is very, very large, such that the probability of even one planet colliding with another is negligible.
But that doesn't mean that Earth is entirely off the hook.
So somewhere around a 10% chance or so that the Earth would get ejected with the sun and the solar system in one of these tidal tails.
And then we would be far away, and we'd sort of have, you know, a bird's eye view of our galaxy. So really the main implication for what we will see on our sky has to do with how the orbit of our sun is changed during the collision.
Stars and planets can pass by each other without incident, but not gas. A galactic collision is really about smashing gas.
Both Andromeda and the Milky Way have a fair amount of gas in them. So all of the gas is going to collide, it's going to shock, it's going to immediately make a lot of stars. We'll probably get, I don't know, 10 billion stars made fairly quickly.
This is what we call a starburst. And this rampant star formation seems to be an indicator of galaxy interactions.
So if we were on a planet within one of these galaxies, the night sky would be very dramatic, especially when the starburst is going on. It would just be lit with the fireworks of all these massive stars that are being born. In general, it wouldn't necessarily be dangerous unless you were nearby one of those regions where all the stars are being born.
But once the galaxies combine into an elliptical galaxy, star formation slows down.
You go from a normal galaxy minding its own business, it crashes into another one, you have this huge amount of star formation, this dramatic starburst, but then in a relatively short period of time, all the gas is used up, all the fireworks are over, and the galaxy just basically goes on its merry way, not doing much of anything.
The merger of the Milky Way and Andromeda, dubbed Milkomeda by some astronomers, will also undergo the merger of their dense cores, each harboring a black hole.
The supermassive black hole from one galaxy finds the supermassive black hole from the other galaxy. They come together, they become a bound pair, and then the orbit shrinks, and they merge. And then you get an even bigger supermassive black hole.
This process is violent, and during that process, gas may feed the black hole and produce the appearance of a very bright quasar.
But the greatest danger to Earth during the collision of the Milky Way and Andromeda galaxies is something completely unrelated to the galactic collision. As the new galaxy is being born, our sun will be going through its death throes.
The analogy of life works really well for stars. They're definitely born. There's a point at which they start and they turn on, where they're converting hydrogen to helium and extracting energy. They go through middle age as well. They tend to swell up, they get a little bit brighter, and then towards the end of their lives, they really change dramatically.
As the sun dies, it runs out of its fuel source, hydrogen.
It now becomes a red giant star. Its size will extend all the way out to where the Earth is currently orbiting away from the sun. So it'll be around 90 or 100 million miles in radius. That's not good for life on Earth.
The Earth will lose its oceans, it will lose its atmosphere, and it really won't be hospitable for life.
Provided we can make it this long, billions of years in the future, we'll have to have either colonized nearby star systems or built some kind of artificial planet further away from our star so that we could be at a nice, safe distance.
Though our neighborhood may have become a lifeless hot zone, astronomers predict conditions in the new Milkomeda galaxy will be conducive to life.
There's going to be close to somewhere around 1 trillion stars in this merged galaxy. And these stars are still going to have planets. even if only a small fraction of the planets are habitable. The numbers are so overwhelming that with conservative estimates, it's expected that you would have to have life somewhere in Milkomeda, if not many places within this merged galaxy.
And in our universe, the most fundamental merger is that between death and life. The host of collisions between stars, black holes, and even galaxies represent the most violent of events that bring on rebirth.
And despite everything else going up in flames, it survived.
Weird.
We had a shiny body, we had smelly blood, we had crystals in the blood.
Weird.
So I fell 18 floors. I still can't believe I survived.
Weird.
I was told I'm part human and part extraterrestrial.
What?
I couldn't believe what I was listening to.
I was absolutely gobsmacked.
No one knew what was going on.
God, that's not supposed to happen.
Can science separate the unbelievable?
I don't believe in ghosts, but I know what I saw was real.
From the downright impossible.
This creature is something that you have never seen before.
Or is it all just
really weird, or what?
The new season of Weird or What? Thursday at 9, exclusive on Discovery Science.
The following program contains scenes which should not be imitated.
Welcome to the 2011 U.S. Anvil Shooting Championship. These anvil shooters have gathered from around the country to square off in this heavy metal battle royale to see who can launch an anvil the highest. Passion, engineering, and powder are about to explode. This is Flying Anvils. Here in Farmington, Missouri, home of the 2011 U.S. Anvil Shooting Championships.
Shooting anvils is like fireworks on steroids.
Might be a little crazy in some people's eyes, but it's a lot of fun.
Man, it just never gets old. For centuries, blacksmiths have entertained crowds by combining anvils and gunpowder. But it's only in the past few decades that anvil shooting has become a true organized sport. I know this might look like a crazy pyrotechnics playground, but there are some serious rules to follow. Here's how it works. First, take 2 steel anvils. The base anvil is set upside down, and a 100-pound flyer anvil is placed on top. These anvils have a small cavity called a powder pocket, which holds a fuse and 1 pound of black powder, 3 times more powerful than a shotgun blast. Launches are scored on height and accuracy. 1 point for every foot of elevation, but minus 3 points for every foot it lands away from the base. Holy crap! Each competitor gets 1 chance to fire, with the 2 highest scoring teams advancing to a head-to-head championship round. Let the Anvil games begin. First up, Team Bollinger, led by David Bollinger. David Bollinger hails from Harrison, Michigan. he's wasting no time using his tamper to level the ground. This is a key strategy. An anvil that is even slightly unbalanced will land multiple feet from the base, which leads to huge penalty points.
We are dead on when we cross the cavity axis, so it looks nice. I don't even want to touch it.
Fire in the